This is Anand Pai from Academy in Pursuit of Engineering Excellence. Today we will continue with fluid mechanics, in that chapter 3, fluid kinematics, and today we will discuss about acceleration in Eulerian framework, total acceleration and material derivative. Okay. So one of the main thing here in this topic is that you have to take a pen and a paper to write down all the equations, because until you write down equations people will not understand, students will not understand until you take it down on a paper. So kindly take a paper and a pen and sit for the video. Okay, so let us see what is that. Okay, first of all we will see what is acceleration in Lagrangian framework. Okay, in Lagrangian approach, if we recall from the previous video, you can see the position of the individual fluid particle is specified as a function of initial position and time. That means S is a function of, S is a vector which is given as a function of original location and time. So we can say in terms of vector quantities like this, that is x, y, z are the position at any time, and x0, y0, z0 is position at the initial time, which actually says the what is the particle. It gives the particle its name. Okay, so like that we get this. Okay, and velocity we can easily find out by differentiating with respect to time. Acceleration we can get by differentiating velocity with respect to time. Now if you observe, this is a constant for a particle. If you see x0, y0, z0, if you fix a particle, this is constant. So what happens, my velocity is a function of s. This s is actually function of only time. It is not function of this because it's a constant for a particle. So for a particle, velocity is just the derivation or derivative of this, that is equal to ds by dt. I can easily say here this is equal to ds by dt, because this is the definition of differentiation. Okay, and this I can say is equal to dv by dt, which can be equal to d square s by dt square. Of course these are velocity, these are vectors. Okay, so that has to be understood when we go with Lagrangian approach. It is easy here. Okay, if the particle is specified, very important, the particle has to be specified. For a particle, this is how we find the velocity and acceleration in the Lagrangian framework. Now let us see acceleration in the Eulerian framework. Now if we say acceleration in the Eulerian framework, we can see that actually in the Eulerian approach we have velocity which is specified at every location of the flow field. Okay, so if you give the flow field, for example, if I have a nozzle or a pipe or anything, we have at every point the velocity specified. Okay, it is not for the particle. Okay, if I say this is the position in the space, after with the time at that space how the velocity is going, that is being specified. So here what happens, velocity, when you say velocity is a function of space and time. Now that means velocity v is u v ui plus vj plus wk, where u is a function of time. Okay, so what is happening here is this u is actually equal to dx by dt, and what this v is dy by dt, and this w is dz by dt. Okay, and now the acceleration becomes a bit complicated. How? Because velocity is not just a function of t here, it is the function of x as well as y as well as z. So it becomes complicated. How? When you say the velocity like this, we have to take dv by dt is nothing but change of velocity with respect to time, partial, into dt by dt. This is the expansion we get from basic mathematics. Okay, so like this, if say function z, okay, z is a function of say x and y. Okay, then what is dz by dx? Dz by dx would be dou x by dou z by dou x, I'm sorry here, it would be dou z by dou x into dx by dx plus dou z by dou y into dy by dz. Okay, this is how it is going. So similar way, here we have, this is a function of 4 variables. So it is dou v by dou t into dt by dt plus dou v by dou x into dx by dt, dou v by dou y into dy by dt plus dou v by dou z into dz by dt. Now if you see, this dt cancels, and what is dx by dt? Dx by dt is u. So we can write this as like this. Okay, so this particular thing we can write it as dv by dt. I can write this as equal to dou v by dou t plus, here I can write, instead of this I can write u. So u into dou v by dou x plus, here this one I can write it as v because dou y by dou t is v. So dou v by dou y plus, here this is w, correct, this is w. So I can write this as dou v by dou z. Okay, so let us see how we do it further. Okay, so this is the general case. Now v, you have to keep in mind, v is again ui plus vj plus wk. So this becomes much bigger actually. How it becomes bigger we will see. Okay, so I will go now with the very from the first principles. Okay, that is from the very basics. Let us derive this. Okay, the acceleration, this is actually acceleration. Okay, this is actually acceleration. How do we come with that we will see now. Okay, so now first of all you have u, v, w. Okay, u is a function of x, y, z, t, v is a function of x, y, z, t, w is a function of x, y, z and t. Now if I consider the change in u, say if u plus delta u, a change in u can happen when it goes, this u goes a bit ahead in space, by delta x in space plus y plus delta y in space, that is another point or another time, we will see that. We can write this as z plus delta z in, and then t plus delta t. That means I am going ahead in space and time, or time, one of the two or both together. Then I have u plus delta u. That means I am moving, I am changing my u. Okay, and similar way I can have v plus delta v is equal to v of x plus delta x, y plus delta y, z plus delta z and t plus delta t. It is very important that we write it, students. Although it is, we may think it is repetitive, writing will give you an idea. Okay, engineering cannot be read, it has to be written. Okay, only then you will get most of the idea, and once you write this like this, it is enough. Okay, all the concepts will be clarified, and also the problems what you are doing can be done very easily if the concepts is right with you. Okay, so this equations I will call, I'll make it like this. Okay, I will call this as 1a, 1b and 1c. I want you to write this in your paper, and if I'm fast, then pause this video and write it on a paper, because I'm going to refer to this later on. Okay, so please write this down. Okay, and pause the video and write this down. Okay, so now let us go with Taylor series expansion. Let me go with Taylor series expansion. Just refer to how Taylor series is done, because mathematics is very important for fluid mechanics. Okay, so if you are not comfortable with Taylor series expansion, go back to mathematics and see it once. Okay, now if I see the Taylor series expansion of u plus delta u, if I see the Taylor series expansion of u plus delta u, this can be written as u of x, y, z, comma t plus, here we can write this as dou u by dou x into delta x, first order terms. These are the first order terms in the Taylor series expansion. Similar way, dou u by dou y into delta y plus dou u by dou z into delta z plus dou u by dou t into delta t plus further I will have terms like dou square u by dou t square into 1 by 2 factorial into delta, if I say not t, if I say x first initially, x square into delta x the whole square and so on, which I will remove this and I will write these are higher order term which I am going to neglect. Okay, hot means higher order terms which I am going to neglect. Okay, so this I will call it as 2a. Okay, this is the equation 2a. Similar way I can write v plus delta v. Similar way I can write v plus delta v as, I'll write just v because v is x, y, z and t. That is very important to understand. Okay, then dou v by dou x into delta x, because v is a function of x also, is it not? Similar way, dou v by dou y into delta y plus dou v by dou z into delta z plus dou v by dou t into delta t plus the higher order terms, which is neglected because it is very small. This we will call it as equation 2b. Then similar way w plus delta w. This w plus delta w can be w plus dou w by dou x into delta x plus dou w by dou y into delta y plus dou w by dou z into delta z plus dou w by dou t into delta t plus the higher order terms, which is going to be neglected because it is very small. Now we have u plus delta u in terms of this one. So now in addition, if I see what is delta t, if I see what is delta t or delta x, if I see everywhere I get delta x, is it not? This delta x can be written as u into delta t, because delta t, delta x by delta t is u, correct, when limit tends to 0, but delta t we will put a small one which where it is linear. Okay, then delta y is equal to v into delta t. Fine. Then here the assumption is in the time delta t v remains constant. Okay, so we have to take a small delta t. Okay, and w into delta t, correct. This let us put it as equation number 3. So now let us substitute this equation 3's into equation 2's. Okay, equation 3 into equation 2's. Okay, so let us see that. That's why if you have to pause this, if you have not written this down, please pause the video and write it down. Okay, this is practice. Once the practice is done, you will be strong in understanding what is acceleration, and also you will be able to solve a number of problems. Okay, and this is the basic of fluid mechanics. This is the first thing in fluid mechanics that one has to understand. Okay, so now substituting, if I substituting equation 3 in equations 2, okay, in equations 2, because there are more than one equations, I can write like this. Okay, wherever delta x is there, I want to, first we will say 2a we will see. Okay, then we will see other things. Okay, 2a if I see, we will have u plus delta u, we are neglecting the higher order terms in that, is equal to u, which is a constant, u is there. Okay, not a constant, it's variable with respect to x, y, z and t. Now here this would be dou u by dou x, and what was delta x? Delta x is nothing but u into delta t plus, similar way, dou v by, in the second one it is dou u itself, in the first equation it's all u. Okay, dou u by dou y into v delta t plus, I can have dou u by dou z into w delta t, correct, plus dou u by dou t, and there is always a delta t there. There is no x, y, z, so we need not worry about that, right? So now if you see here, u and u cancels. Then we will divide the whole thing by delta t. We will get this as delta u by delta t is actually equal to u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. This we have got dividing by delta t. Okay. So similarly, I can write delta v by delta t is equal to u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t. Okay. Similarly, another way, delta w by delta t, I can write this as u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z plus dou w by dou t. Now, if I say in limit delta t tending to 0, in the limit delta t tending to 0, let me use this 3 is over, this is 4a, this might be 4b and this may be 4c. Okay. So now in the limit delta t is equal to 0, this will come as d. Okay, because limit delta t tending to 0, delta u by delta t is actually du by dt. So du by dt is equal to u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. Let me put this as 5a. Okay, similar way I can write dou v by dv by dt. It's a exact in the sense it's not a partial one. Okay, here everything is partial. Okay, u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t. It is very important to write this. You may feel this is unimportant because it's coming continuously, but it is very important to write this to get that practice. Okay, because we make mistakes otherwise. Okay, this is also related to skills. Okay, so this will be dou w by dou x plus v into dou w by dou y plus w into dou w by dou z plus dou w by dou t. If you have not written, please pause the video and write these down. Okay, so this completes, these are the accelerations we can say. Okay, this is actually equal to ax, acceleration in the x direction without a vector. It's not a vector, it's a scalar because everything is a scalar quantity here. Okay, only v is a vector quantity. Okay, but v, when I say v is equal to ui plus vj plus wk, this j, I, j, k are unit vectors, u, v, w are scalar. So everything is scalar here. So here this is ay and this is az. Okay, so this is very important. These are acceleration term. So now my total acceleration, we call it as a total acceleration, or the acceleration vector, I'm sorry, not the total acceleration. So if I say acceleration vector, the acceleration vector A is given as axi plus ayj plus azk. I hope it is clear, students. So this is how the acceleration is written here. Now this d, actually the previous slide when you have this acceleration du by dt, can be written in terms of capital D. Instead of that, I can write it in terms of capital D. So I can write AX as du by dt. And this is called the material derivative. So AY is equal to du by, AY is equal to dV by dt, and AZ is equal to dW by dt. Now this particular thing is called the material derivative. Very important. This is also important in heat transfer as well. Okay, derivative, heat transfer, mass transfer, a lot of places this material derivative is used. Okay, so now this material derivative is actually just a second, students. Yes, I have written it down properly. So I can write this material derivative as dou u by dou t plus u into dou u by dou x plus v into dou u by dou y. I am writing it again, reiterating the purpose of repetition. Okay, delta z. Here I can write dou v by dou t plus u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou y. Okay, similar way again we have dou w by dou t plus u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z. Now this is how the acceleration comes. Here there are two parts here. These parts, these three, 1, 2, 3, these are called temporal acceleration. These are called temporal acceleration. And these are called convective acceleration. These are called convective acceleration. Very important. Okay. Now what is happening here? U is carried, the gradient of U is carried by U. Now this is way, or gradient of U is carried by V, gradient along the x direction. So this is very, very important in a lot of places. Okay. So especially in heat transfer or mass transfer, these kind of things, it's very, very, very important. Okay. And this forms the basis of fluid mechanics. If you understand acceleration, you understand fluid mechanics later on. Okay. So any doubts you have in this, kindly put it in the comments. I will answer this in the subsequent videos. Okay. And kindly subscribe to my channel and click the bell icon so that you could get the further videos. Okay. Any suggestion, anything, you can put it on the comments section. Okay. Thank you, students.